Soon we'll have the spaceships that can take humans to Mars. And we have developed habitats for Mars. Ultralight prefabricated inflatable structures where you can live safely, protected under several meters of regolith from cosmic radiation, meteorites and cold, with integrated greenhouses for self-sufficient supply of oxygen and food. But the remaining question is, how can the human body endure the extreme hardships of a month-long journey to and from Mars, exposed to a high dose of cosmic radiation and microgravity, where muscles and bones gradually weaken? With a direct home and transfer on Starship, it will take 7-month journey to Mars and another 7 months for the return. The longest duration humans have spent in space so far was Frank Rubio's 371 days on the ISS in 2023. However, the ISS is partially shielded from cosmic radiation by Earth and remains within the protective range of Earth's magnetic field. During a journey to Mars, the radiation intensity would be about 3 times higher. On a round trip to Mars, the crew would receive 4 times the total radiation dose that Frank Rubio experienced. Additionally, the total radiation dose is increased by exposure on Mars when crew members leave the safe habitat to explore the Martian surface. Another problem is the negative impact on physical performance due to microgravity in the spacecraft. Astronauts returning from the ISS already faced problems after much shorter stays, such as muscle atrophy, reduced bone mass, heart shrinkage, and vision issues. For example, they were too weak to stand on their feet when they returned to Earth. On Earth, this is not a problem as they can recover within a few weeks under careful medical supervision. But how would they carry out their challenging mission or even survive under the harsh conditions if they arrive on Mars in such a weakened state? To provide effective radiation protection in a spaceship, a hull about 2 meters thick with water or 4 meters thick with regolith is required. A normal spacecraft, such as SpaceX Starship, equipped with such radiation shielding would be far too heavy to leave Earth's gravitational field. With currently foreseeable technology, only a rotating habitat with a resulting centripetal force can simulate gravity to avoid the health disadvantages caused by microgravity. I don't want to go into detail about the challenges of artificial gravity here and refer to numerous other videos that address this topic. Just this much. In order to avoid issues with dizziness, motion sickness and Coriolis force, a rotating spacecraft that simulates artificial gravity should not spin faster than 3 revolutions per minute and therefore would need a radius of 100 meters to generate Earth-like gravity. A rotating passenger compartment of this size would make a spacecraft too large, bulky and heavy to launch from Earth's surface and to even reach low Earth orbit through the atmosphere. Therefore, since the 1980s, there have been concepts for a marscycler, of which Buzz Aldrin's concept is the most well known. A marscycler describes a highly eccentric elliptical orbit of a spacecraft or a space station, where it regularly comes close to both Earth and Mars in its orbit around the Sun. This marscycler, supported by the gravity of the Sun, Earth and Mars, can maintain its stable orbit permanently without additional energy input, or at least only minimal energy for small course corrections. This is independent of the mass of the cycler, allowing for extensive life support infrastructure and good radiation shielding. It only requires a one-time energy input or a one-time delta V to accelerate the cycler from its origin into the desired orbit. At continuous operation, a small space taxi flies to the cycler when it's closest to Earth, leave it when it's closest to Mars, and do the same in reverse for the return trip. Most of the infrastructure would be on the cycler, especially the radiation protection. The cycler could also rotate to provide artificial gravity and even include a greenhouse for self-sufficient production of food and oxygen. Sending a spacecraft to Mars with a rendezvous on the cycler in between requires more delta V than a direct Hohmann transfer. However, if the cycler contains all the necessary infrastructure, especially self-sustaining greenhouses for food and oxygen, the payload on the space taxi can be much lighter than in an ordinary spacecraft, saving fuel even at higher delta V. Calculating and determining the optimal cycler orbit so that the cycler vehicle meets Earth and Mars at the right time and optimally utilizes the gravitational fields is a challenging task. I won't go into detail on this in this video, because this video mainly is about the design of the cycler space station. There are numerous other videos that deal with this topic. I would especially like to highlight the channel Science Meets Fiction by Axel Hauff. While Buzz Aldrin's concept and the calculation of the cycler orbit are brilliant, the presented spacecraft does not feature many novel ideas, and it even doesn't seem to feature sufficient radiation shielding and artificial gravity. The challenge with previous cycler concepts is the enormous energy required to transport all building materials into low Earth orbit, to assemble the cycler station and accelerate it into the correct orbit. Providing sufficient shielding from cosmic radiation additionally significantly adds to the required material. And here comes the novelty of our Trinity cycler concept. Our solution is a tensegrity structure of ultralight prefabricated inflatable modules connected by tethers using centrifugal force as a structural element. All the shielding material, and also preferably water, will be mined from an extraterrestrial source. The lightweight inflatable modules will be transported to an asteroid that already has an orbit very close to the optimal cycler orbit and passes by Earth close periodically. The modules will be assembled on the asteroid and its regolith filled into membrane bags used as shielding material. Since the regolith cover also protects from micrometeorites and space debris, the membrane structure can be much simpler and lighter than that of the inflatable module on the ISS, which needs to withstand such impacts. The complete cycler will have a high mass, but very little of extra delta V will be required to bring it from the nearly optimal asteroid's orbit into the optimal cycler orbit. There are thousands of asteroids in an elliptical orbit between Earth orbit and Mars orbit. Therefore, there is a good chance that at least a few of them have a suitable orbit and structure to serve as a raw material source and launch base for the completed Mars cycler. One such candidate is the asteroid 25143 Itokawa, that also contains some water. As we can see, the orbit of the asteroid Itokawa deviates only slightly from the S1L1 cycler orbit. The inclination of its orbit is also very close to the orbital inclinations of Earth and Mars. Therefore, only a very small delta V is required to transfer the complete space station from Itokawa into the desired orbit. A torus-shaped rotating space station with the required diameter and sufficient protection against cosmic radiation has enormous mass. Two separate rotating passenger pods, connected by a truss structure with the same rotational diameter, have far less mass. However, the truss also requires some mass. The two passenger pods can also be connected by a cable which has very little mass and barely increases the total mass when the diameter is expanded. However, such a cable is not very stable laterally, making it susceptible to vibrations and oscillations. Therefore, we connect three passenger pods with cables in a triangular formation. This triangular setup is much more stable against vibrations than a simple cable connection between two bodies. But even in this triangular configuration, small vibrations parallel to the axis of rotation can still occur. To counteract this, we expand the cable connections into a double tetrahedron formation. Centrifugal force becomes a structural element in the system. The rotating passenger pods pull on all cables due to the centrifugal force. The upper and lower cable groups each pull from above and below on a central truss, which is the only component in a static system that also has to bear compressive forces. Our space station consists of following elements: 3 rotating habitat pods and a central pod for experiments in microgravity, all wrapped into bags filled with regolith for protection from cosmic radiation, meteorite impacts and extreme temperature, plus an external layer of reflective membrane. Tubular nets of cables function as tethers with centrifugal force as a structural element. Within these cable tunnels, we also guide the movable ballast that adjusts the center of gravity and free commuting elevator cabins between the pods. The tensile forces of the cable net tunnels result in a compressive force on the central truss tower, which is the only rigid element, and in combination with the cables and centrifugal force forms a tensegrity structure. A truss framework on the bottom side is connected via a flexible magnetic ring and does not rotate. Here, up to 3 spaceships can dock on. It hosts an elevator cabin that can not only move up and down, but also rotate to dock on the spaceship in 3 positions, and it also can spin freely as soon as it docks onto the spinning space station. In each habitat pod, behind the thick layer of regolith, there is a greenhouse for self-sufficient and sustainable production of food and oxygen. Since the triangular formation of the marscycler station strongly resembles the Christian symbol of Trinity, we call it the Trinity marscycler. At the top there is a light, thin, rapidly rotating mirrored foil. Due to the centrifugal force, this foil stretches into a plane inclined at 45 degrees to the Sun. Thanks to the stabilizing gyroscopic effect, the rotating mirrored foil maintains its orientation toward the Sun independent of the movement of the rest of the space station. A flexible magnetic ring bearing enables the rotation axis of the mirrored foil to be adjusted independently of the station's rotation axis. The rotation axis needs to be adjusted in one complete cycle only within every 1.5 years to follow the Sun, which requires minimal energy due to the foil's low mass. The mirrored foil reflects sunlight onto a group of 3 fixed rectangular parabolic mirrors. Their reflective coating is made of silver, which reflects very little ultraviolet light. From there, the light is concentrated so that it passes through a small opening into the habitat pods and is then scattered back onto the greenhouse area by reversing the light cone inside. It is important that the light entry opening remains small to minimize exposure of the window area to cosmic radiation and micrometeorites. Remaining surfaces are covered with photovoltaic cells, which continuously generate electricity from the reflected sunlight.